In previous videos, we talked about some of the basic materials, including the basics of vectors. In particular, we discussed the subtraction and addition of vectors. We also discussed how to find the length of a vector, and we discussed the unit vector. We also introduced the concept of inner product of vectors and the orthogonal vectors. And we then extended the concept, and we talked about the inner product of functions. And from there, we introduced a new concept called the orthogonal functions. Now, before being able to proceed to the orthogonal series expansion, there are a few more concepts to discuss, including the orthogonal sets, infinite sets, norm and square norm of a function, and finally the orthonormal sets. In this video, I'm going to be talking about the orthogonal sets, and the rest of these concepts will be covered in the next few videos. Now let's start with the concept of orthogonal set. So by definition, a set of real valued functions like phi1, phi2, phi3 all the way to phi n is called orthogonal on the interval a to b if each pair of the functions like phi I and phi j is orthogonal on the given interval a to b. And basically what it means is that if you have a set of functions which consists of any number of functions like n functions like phi1, phi2 all the way to phi n, where these functions are defined on the interval a to b. For example, let's say this is phi1, this one is phi2, and let's say this constant function, this one is phi3, etc. Now for this set of functions to be orthogonal, we need any given pair of functions that you pick, that pair of functions need to be orthogonal. That means that, for example, if you pick phi I and phi j, those two functions need to be orthogonal on the interval a to b. And if you have watched the previous videos, now you know that for two functions to be orthogonal, they just need to have a zero inner product. So that means that phi I and phi j need to have inner product of 0. And again, by definition, the inner product of two functions is just the integral of their product over that given interval. So for example, inner product of phi I and phi j is an integral over a to b of the product of those two functions, phi I and phi j. So phi I times phi j integral over a to b. And if that integral equals 0, that means that inner product of phi I and phi j equals 0. So, and if you have the same 0 inner product for any pair of functions that you have in your set, then that set is going to be orthogonal. Now let's take a look at a simple example. We have a set consisting of two functions, 1 and x, and we want to see if this set is orthogonal on the interval -1 to 1. So if I draw these functions on the coordinate plane, it's going to look like this, where this is the y equals x, and this is the constant function of y equals 1. So we have these two functions defined on -1 to 1, and we want to see if these two functions form a orthogonal set, basically. So in order to figure out if this set is orthogonal or not, you wouldn't really need to draw these functions here. I just drew that here to give you some more insight how these functions look like. But at the end of the day, you just need to see if the inner product of each pair of functions that you have in that set is 0 or not. And since we have a set with two members here, we have just one pair of functions to investigate. So we have 1 and x, and we just need to see if the inner product of 1 and x is 0 or not. So that's our mission here. And by definition, the inner product of 1 and x is going to be the integral of 1 multiplied by x. So the product of these two functions, 1 times x dx, over the given interval -1 to 1. Right? If we calculate this integral, it's going to be integral x dx from -1 to 1, which is going to be half x squared from -1 to +1, which equals half 1 squared minus 1 squared. And if you calculate that, you're going to see that it's going to be 0. So this was a simple example, since our set consists of only two members here, so we have just one pair of functions to look at, and we have seen that that pair of functions has a inner product of 0. So the conclusion is that this set is orthogonal. Now let's consider a new example. We have a set consisting of three members, 1, x, and x squared. So you can consider this as an extension of the previous example, and we want to see if this new set is orthogonal on the interval -1 to 1. So if I draw those functions on the coordinate plane, I'm going to get something like this. So as before, this one is y equals x, this constant function is y equals 1, and this green function is the new function that we have added to our set, y equals x squared. So in order to see if this set is orthogonal or not, we need to look at the inner product of any pair of functions that we can imagine in this set. So let's see which pair of functions we have. So we have 1 and x, so we need to investigate the inner product of 1 and x. The other one, so this one was 1 and x, and we have 1 and x squared. Similarly, we have x and x squared. So we have three pairs of functions to investigate. So from the previous example, we learned that inner product of 1 and x equals 0 on the given interval of -1 to 1. So this one is checked. So we just need to look at the inner product of 1 and x squared and x squared. So let's start with x and x squared. So inner product of x and x squared is going to be the integral of their product, again, x times x squared dx over this interval -1 to 1. So it's going to be integral of x cubed dx from -1 to 1 equals 1/4 of x to power 4 from -1 to +1, which is going to be, if you calculate that, 1/4 of 1 raised to power 4 minus -1 raised to power 4, which is going to be 0. So this pair of functions also has a 0 inner product. So now let's calculate the last inner product, 1 and x squared. So inner product of 1 and x squared, again by definition, is going to be the integral of their product, 1 times x squared dx from -1 to +1, and is going to be integral of x squared dx -1 to 1, which is going to be 1/3 of x cubed from -1 to +1, which is going to be 1/3 of 1 to power 3 minus -1 to power 3, which is going to be equal to 2/3. So this pair of functions then has a non-zero inner product. The inner product is going to be 2/3. So this inner product is not 0. So the conclusion is that the set is not orthogonal.